And start the presentation. Yeah. Okay. So is this slide visible? Hello?
Yes, sir.
Yeah, right. So, in the last class, the last few lectures, I think almost like 4 lectures, we almost discussed about various aspects of operating system at a very broader perspective from introductory point of view. It's nothing but what all about the operating system is, what it will do, what are its functionalities or services it provides and all, and how it coordinates the hardware and as well the user requirements and all. And from both the perspective, what are its responsibilities, objectives and all. So, and how the user applications access the operating system in the form of system calls, system programs, and so on. So all these aspects we discussed, and also to take care to perform all these various to carry out these various services to user programs, or from the system point of view, it has to provide certain services and to handle all these things. So first of all, how do you design or how do you implement an operating system, design an operating system? What are its various approaches for designing the operating system? Because it's a very complicated one, as you have seen. So it has to handle many things in a computer from a user perspective and from system perspective and all. So therefore, how do we go about, or how do you design an operating system for certain aspects, for certain objectives? Because it varies depending on the underlying hardware and from the applications you view, and from the environments you are using, because various environments we are experiencing the computing nowadays, right? Like in the case of desktop systems, the objectives are different. If you go to the mobile platform, where the need or the applications what we use through mobiles are different. So there are and the scenarios are different. The computation or computing environments are different and all. So in all these aspects, how the operating system, what are its objectives, goals, and all. And then first of all, how do you design these varieties of operating systems for its suitability in the different environments and also all those things we discussed in the last class. And finally, we are discussing about design aspects of operating system. In that we started with a very simple one like MS-DOS, right? Very simple operating system. Then the monolithic operating systems like both Windows and the Unix operating systems. And afterwards, we thought of the good one, or the more, from a flexibility point of view, layered architecture will be much nicer and much it will be much useful in designing operating systems to handle this very complicated process and all. And then the dynamically loaded operating systems, modularized ones, all these things we discussed. And there are few ones were there that I'm just giving you for your self-study. They are like hybrid operating systems. It means that actually whatever we discussed, so hybrid operating systems means a system, the operating system consists of a combination of not a single approach, single operating system. It's like two operating system. For example, your MS Mac OS, iOS. So where it consists of a flavor of microkernel operating system like a MACH Match operating system, and also it contains a flavor of normal BSD Unix also. It's a combination of both will be there. And so likewise, even the operating systems that are supported in our mobile devices like iOS, where for Apple mobile phones and Apple these things, iPads and all these things, the supporting operating system iOS is also of a form of hybrid. basically use the macOS support, and in addition to that, it also uses some other other functionalities and all, which are suitable for more targeted, tailor-made for the mobile platforms and all. The same way for Android operating system also, where the basic operating system that supports will be the Unix one, and that also like modified for targeted for mobile systems, like for in view of power constraints and in view of other limited resources and all. And in addition to that, it also has other components and all. So that way, all these the recent operating systems that are designed for mobile platforms and all. So they are like come under the category of hybrid operating systems, right? And the another thing just I want to mention before going to this will be usually the operating systems when you design for that, the designers will design operating system like they will design with respect to particular computational environment, but at the same time they will be designed in a way to some extent will be generic for the given environment. And in that environment, if you are loading operating system in a particular system, and for that operating system for that in that particular system, so if you want to effectively utilize the operating system, so you need to tailor make the operating system according to the particular system. Like a system may have, for example, whatever the underlying hardware the system has, and what are the requirements from the user applications in that particular system. So by giving those specifications, again, if you compile the operating system, then the operating system will be like a compatible or like a more like tailor-made to that particular system and all. Like maybe, for example, a hardware may contains the like a multiprocessor thing. It may have a quad core or octa core or whatever, and it has whatever the memory requirements and all those things. If you are aware of those things, and if you can provide those are the inputs for giving a proper compiled operating system for a given system and all. So in that case, actually the generic operating system compared to that, first of all, if you run that operating system by providing the specifications means basically the hardware specifications, whatever the operating system should run on that, and then whatever the user applications and user applications, user requirements. If you provide these specifications and then if you compile the operating system, if you run the operating system, then the operating system can generate can be whatever the for that we use some program known to be system generation and all. And using that program, if you run that, it basically provides the specifications, whatever the system, from a hardware perspective, from a user perspective, what are the system specifications required. And in view of those specifications, the operating system will be again like it's not like what the generic system will be that the generic system will be modified to like tailor made to a particular system and for a particular requirements and all. So that is one thing I just want to mention. And other things and all, you please go through that, the hybrid systems, whatever I have mentioned, and like booting the like system at the time, how the operating system will be loaded. So those aspects we discussed even in the initial classes and all. So please go through that, and let's now start the details of the various functionalities in which the operating system is to offer. So under that, actually, first we'll start with in view of processes. That means execution of processes. So what are the the basic objectives or basic functionalities of operating system? How it will support the process execution and all. And so those aspects we'll try to discuss in 1 or 2 lectures and all. So let's start in view of process. It means we have seen that like under the process management, there are several responsibilities of operating systems and all, right? So we'll see one by one over here. And so in this, we'll try to discuss about, first of all, anyway, we already know that what is meant by process and all. Again, we'll reiterate the concept of a process, what it is actually, and then how the processes are scheduled. Because here in a computer, we have a limited resources. We have CPU. Maybe you have one CPU, or it may have a few cores like a quad core or octa core, like a few CPUs and all. And at the same time, we have lots of processes that are ready for execution. And the same way, we have the other resources also. We have the IO devices and we have the other devices, whatever is there. So they are limited in nature, but the number of processes that are executed or will make use of those resources will be more than the number of resources and all. So in that case, we need to schedule these processes to these resources in a way that one thing is that the process execution time will be optimized and at the same time the resources also better utilized. So that way you can see that what is process scheduling and then what are the various operations on the process. We'll see that what are the various operations on the process, like how do you create a process, how do you terminate the process, likewise how a process will communicate. So all these things are come under the various operations. Inter-process communication, as we know that when the process are executing, some process needs information from some other process, right? And so in that context, a process has to communicate with some other process. And this communication may happen within a system or maybe across the systems also. And so under that, we'll see that how the process communication will take place, right? And we'll see the examples, how the process communication, what are the different modes of process communication. We'll see that. And then finally, we'll see that we'll try to very briefly describe about how the communication between the process will happen under the paradigm of client server configuration and all. So these are the various aspects we'll try to discuss under this chapter. And again, just the broad objectives here are, as I already mentioned, introducing the notion of a process. Means what exactly mean by process. We know that a program in execution is known to be a process, right? A program in execution is known to be a process. Otherwise, a program on the disk and all, it's a simply executable code or sequence of instructions and all. And at the moment, once you want to execute that process, then you brought this process into the main memory, and then it will be given access to the CPU. So that CPU access execute the sequence of instructions and all. And the moment once you brought the program into the memory, that means it's ready for execution. So it's known to be a process and all. And then the different features of a process, it includes, as I already mentioned, like scheduling the process that is required, creating a process, termination of a process is required, and a communication across among the processes that also required. And then to explore the inter-process communication, as I mentioned, there are two broader strategies. One is the shared memory concept. That means using shared memory approach, a process can able to communicate. And other one is that the message passing and all. The shared memory, from the terminology itself, here a segment of memory will be shared across the process. So usually we have seen that each process has a specific designated memory address space will be there. And a process should execute only within that address space. It should not cross beyond that. But if your process want to communicate, the one way to communicate the process will be using a shared memory and all. So here in the concept, in the idea of shared memory, we'll see the details later and all. A particular memory segment will be allocated to a multiple process, and then these processes will make use of that particular memory segment for writing the data into that and reading the data from that. So with that, a process can able to communicate using a shared memory concept. And other one is a message passing here. And message passing means here, like the example will be what we already come across in an environment like a peer-to-peer processing or like a client server processing and all. And even other case also where a process want to communicate with other process. So it will first talk to that. Initially, it will establish a connection, and then through the connection using appropriate system calls, the messages will be communicated back and forth and all. We'll see the details later. And then finally, we'll discuss about the communication, process communication in the context of client server systems and all. So these things actually we come across actually the ideas, at least the broader philosophy of this one we discussed at the very first chapter, but here we'll see more details with respect to some well-known operating systems and all. And coming to the concept of a process, and here I'm just here we are introducing the multiple terms. You can see that In the context of batch systems, these processes are viewed as the jobs and all. And whereas in case of time shared systems and the present, the interactive systems, user interactive systems, we'll call them as a task or the processes and all. So all these terms are like more or less, they are interchangeable, because the batch system is at that time, that means at the early in the 80s and all, where most of the computers, they perform the job, they perform the applications. Mostly like the user interaction is not required. They are mostly computational applications and all. So at that time, the user interaction is not required. So therefore, a batch of jobs will be given to the system, and the system will execute one after another, and it will whatever the status, whatever the status of the jobs after completion, that will be written in some other files and all. So that way, the user after some time, they will look at the status of those output files. So with that, he will come to know that whether the jobs are properly completed or not, or what is the outcome. So in that context, we'll say that the processes can be are known to be jobs and all. And whereas at present, the most of the applications are the user interactive applications and all. Or the user want to see how the program is running, what are the various intermediate results and all. And in that context, there's also going to be time shared, because to have the user interactive programs to run, so the CPU has to run the process in a time shared manner. It's not like the way the earlier the jobs are given, like where the job sequence of jobs will be run one after another. It's not that way. So therefore, these terms are like jobs or processes and all. They are like one and the same. They are used. We use the terminology very interchangeably in this yeah, here in this few lectures and all. And we already know that process, what it means is a program in execution. Already mentioned that. And the process, it contains multiple parts, as we already aware that we already come across in our architecture. When you're discussing about the computer architecture, we discussed about some of the details of this, what the process consists of. A program code, as we have already seen, that a text section and a stack. Yeah, if you go to the next part, you can able to see this. This is a process, like overall process, where it contains the text section, which contains the instructions, like, and the data, which contains the global variables and all. And you have a stack. It means that recent activity, or the whatever the program in execution, whatever the data that will be generated, and all these things will be, or if any function calls and all. So all these things will be done, carried out. The related data will be there in the stack. And a heap is nothing but the data that is generated dynamically during the runtime. So that will be there at the heap bundle. So these two are like they are dynamic bundle. So based on the requirement, the stack and heap will grow in opposite direction. And if you look at this program, you can see here and all these are the data, global data. I see that. So therefore, these global variables and also they will be placed over here and all in the data section. And here, this is the data that is within the function call execution. So it will be there in the stack portion and all. And the text portion contains these instructions and all. So likewise, you can see that the process contains the multiple entities, like set of instructions, and the data, and then the current execution information status, and the other things and all. So that's what I mean by there are various parts of process can be viewed like this. And a process is active, as we know that, as we are already aware of that. And the passive entity is nothing but program is a passive entity. That's what a program is nothing but the executable code that it's there in the present in the disk and all. It's a passive entity. And we know this the same thing, like as here you can see, program becomes a process when you load it into the memory. And yeah, what else here? Yeah, how the way we do when you execute the program, it's nothing but, so whatever the program you want to execute. So either in case of graphical user interface, using a mouse, we'll double click that on the program on that icon. So with that, actually the program, that executable, will be brought into the main memory, and then the resources will be allocated, and then it will be given access to the CPU and all. And whereas in case of command line interface, it's nothing but just type the program name, whatever you want to execute, and then click the enter button. Then it will be executed. So that way, the program, the executable code will become a process and all. And then sometimes a single program can have it generates a multiple process. So this we already we are all are aware of that. For example, you have a browser program, right? And then suppose, for example, you want to access some web pages and all, we'll click the browser, and then it means it will be loaded from a secondary to the main memory, and then the browser, whatever the URL you want to access and all, you give the input and it will be brought in. So that way a process is generated. And again, in the next window, again, you want to access some other thing. So you again click the browser and all. Again, the browser will generate one more process, right? And then again, it will run. So here in this, even though all these browsers and all, maybe the instruction part of the code segment may be same, but the other parts of a process, like whatever stack entities and then other heap entities, and those things may be different and all, because the one, even though you are using web browser program, basic program, but the content you are fetching may be different, or the portals you are accessing may be different. So therefore, the same way, for example, using some text editor and all, you open the text editor and then you create some file. And again, use the same text editor, you just open some other file, you open and then you type in some other data and all. So likewise, using a word processor or text editor, you can the same process, the same program will be there, and you access that multiple times. So with that, the multiple process will be generated from the same underlying program and all, right? So that's what mean by a program can have several processes. It means that this is the example to that. Yeah, this we have discussed and all. And then a process, when it executes, it is in a different at different states. And here basically here we are defining what are the various states that the process can encounter during its execution, right? And so these are the five broader, or like at a gross level, these are the five different states a process can experience during its execution. And they are like a new state means when a process is created, we say that the process is in the new state and all. It means the process is created means when you click on the program twice using in the GUI, or in the command interpreter when you enter the command, or when you just enter the name of the program, and then if you enter, so it becomes a new. That means now that the state of a process is created, and it is in a new state. You can say that it's a new state. And then a running state means, suppose a process now it is given to the CPU, and CPU is executing the instructions of a process. Then we say that the process is in the running state. That means when the process is running state means, so at that time the instructions of a process are in execution stage by the CPU. Then the waiting, it means the process may be waiting an event to occur. A process sometimes it will be in the waiting state for some event to occur. So examples will be like process, suppose when it needs IO, for example, at that time the process may be in the waiting state to get the data from the corresponding IO devices. For example, as you mentioned, from a keyboard, for example, a user want to enter some data in a program. A program requires at certain point of a time, a program needs the input from a user and all. So the user will give the input through a keyboard and all. At that time, the process will be in a waiting state, waiting for the input from the keyboard and all. And likewise, the process may be waiting for a file, access a file from the disk and all. At that time also, a process may be waiting at the disk to access the file from the disk and all. Likewise, there are different scenarios. Sometimes a process may be waiting for some other process to send some information, right? Maybe like it is executing at some point of a time, it needs the information from some other process. At that time, the process will be waiting for a message from some other process. So this is So in this context, we say that the process is in the waiting state. And there is another state which is not a ready state. So it means here the process is waiting for its execution, like waiting to be assigned to the processor. That means the process is in the new state. The process is created, and afterwards it's in the main memory, and then it will be like it is in the queue or it is ready for execution. But the CPU is executing some other process. It is waiting for its turn. So in that case, you say that the process is in the ready state. It means that the process is waiting for to be assigned to the CPU processor and all. It's not to be ready state. And finally terminated. Suppose the process has finished its execution. That means the process completes, like reaches to a last statement or last instruction. Then you can say that the process is terminated and all. So these are the 5 broader states where the process visits during this execution. It will be in one of the states and all. So this is the process state diagram. You can see this is the new process. It's a process is created. Then afterwards, process may be there in the main memory if the place is available, or if the space is not available, then it may be there in the buffer in the disk itself. But it is there. It's created. Process is created, right? And then after the once the process is created, then it will be if the queue is available, then it will be admitted into the queue. That is not to be ready queue. That means nothing but it is ready, and it's ready means the process will be kept in a queue, and at some point of a time, this process will be given access to the CPU and all. So then we say it's the ready state and all. So first is the new state, then afterwards it will be when the process will be kept under in a queue and waiting for or maybe or further in the subsequently it will be allocated to the CPU. Then we say that it's in the ready state and all. And the running means only one process will be there because the CPU can access only one CPU, one process at a time. Like so that particular process we say that it's in the running state. There may be multiple processes have in the ready state, but the running state will be given to only one process. Only one process can have a running state, and likewise, yeah, this one. And afterwards, waiting. As I mentioned, that waiting state process is waiting for certain event to occur. So that waiting that event maybe have different types. May have IO and may have some other thing. As I mentioned, that the message has to come, or it may be waiting for some signal for something else. So likewise, the process may be waiting for different reasons and all. And that event occurs like when the IO is completed or some signal has arrived or some other thing happened, then the waiting from it moves from waiting state to again the ready state and all. Because now the desired IO is completed or the desired signal has been received and all, then the process which is waiting, it will be again go back to the ready state. It means that now the waiting has been done, whatever it's done, and now the process still have some more statements were there for its execution. So therefore, it will go and wait for the it will go in the and it's there in the ready queue and all. It will be there in the ready queue. So and then sometimes no, then when the process is completed, that means when it executes the last instruction and there is no more instructions to execute, at that time the process will be terminated. So usually the process will when terminates, it executes a system call known to be exit system call. So usually, sometimes no, like the programmers will write explicitly the exit system call. So it means that the process will be terminated. And sometimes no, even just a written statement itself will be identified by the operating system that or like a compiler that a process has reached to the last statement. So therefore, it has to be terminated. So therefore, the compiler will introduce this system call, the exit system call automatically. So the programmers need not they will you can the programmers can keep can introduce can place the exit system call, can place the corresponding exit function. So instead, actually, if they are not done also, then the compiler will take care, and the compiler will come to know that this is the last statement of execution. Then it introduces the corresponding statement where it's nothing but system call, and with that system call, it exits. That means it will terminate and all, right? And Yeah, and here one more thing, there is another transition I have not mentioned, like interrupt. So when the process is execution, it's not if it's a running state. It means that the sequence of instructions are executed by the CPU. And when the process is in the when the process is in execution, in the running state, the process may be leaving the running state because of different reasons. So one reason is that the process may be leaving or switching from running state to some other state, maybe going to the waiting state, where at that time the process needs some IO. Suppose, for example, is executing some sequence of instruction, and when it encounters instructions such as scanf function, so it means that that particular function is nothing but input from a keyboard. So therefore, the it's nothing to do with the CPU. So therefore, excuse me. సార్ క్లాస్లో ఉన్నాను సార్ కాల్ చేస్తాను సార్ తర్వాత సో yeah, it's in in the running state, when the process as an example I mentioned, like a scanf function, when it encounters, it requires the input. So therefore the CPU from the process will be switched from the CPU, and it will be and it will be the operating system will take the process out of the CPU, and it will be given to the it will be maybe the process may be waiting for the keyboard, waiting for the keyboard device controller to get the input from the keyboard controller and all. So at that time, the CPU will fetch the next process that is there in the queue, by using a scheduler dispatch. It will just take the next process, whichever is waiting, and that process will be running. So there's one way that actually in the when the process is running, because of IO or because of some other thing, a process may leave the CPU, and it will be waiting for that particular activity should happen, or that particular event should occur. It may be IO, or it may be some signal, it may be some other thing, whatever it is required. And sometimes a process is running, for example, and some interrupt occurs. Some interrupt signal occurs. Interrupt signal means a CPU is executing its user program, and some signal is arrived to the CPU. It's known to be interrupt. That interrupt has seen that it may be the external interrupt. That means the devices or peripherals of a computer may need some service from the system and all. At that time, they will send the signal. So with that, the CPU will realize that yeah, there is some signal from the interrupt pin. So it means that immediately the corresponding operating system service routine has to be executed for handling that particular interrupt and all. So at that time, whatever the process right now is currently running, so that process will be not terminated. Process will be suspended, and here the process, if there is no interrupt, then the process will continue to run. But because of the interrupt, the process will be suspended. So therefore, the process will be kept in the ready queue back, right? Because the process is running and there is some emergency or some signal arrived to the CPU through the interrupt pin. So at that time, the operating system will activate and then see that what is the reason for the interrupt and how that interrupt has to be handled. So then the CPU has to run the operating system code, the corresponding code. So therefore, the right now, whatever the current process is running, that process will be suspended and it will be pushed back to the ready queue, because reason is that because the process, if there is no interrupt, the process will run further. So therefore, it will be pushed into the ready queue, and then the CPU will execute the corresponding operating system service routine for handling that particular interrupt. So therefore, this transition, the interrupt transition is nothing but when an interrupt occurs, at that time the process will be switched or process will be suspended and will be placed in the ready queue. And that interrupt will be sometimes no timer interrupt also may occur. Suppose if it's a time sharing system, right? And the process is running, and each process will be given some time slot, like 100 milliseconds, 50 milliseconds, and so on. And the timer will be set to that particular time count. And during that time count, if IO required, then anyway process will be suspended and it will be given to, it will be waiting at the IO. And a process has still it can able to run. If it runs, if there is no IO and all, then beyond 100 milliseconds, beyond 50 milliseconds also process can execute. But as it's a time shared system and all, each process will be given some time slot. So therefore, at the end of a time slot, the timer will generate an interrupt. It will generate a signal indicating that yeah, the time slot has been over. So now the process, currently running process, will be suspended and it will be pushed to the ready queue, and the next process will be fetched if it is a timer interrupt, right? Because anyway, that will be again has to be that has to be realized or handled by the operating system, because the moment once the interrupt has occurred and the operating system will take over, and the operating system will push the present process to be in the ready queue, and it will analyze that what is that interrupt. If it is a timer interrupt, then operating system will fetch the next process from the queue, from the scheduler queue, from ready queue. And if it is some other interrupt and all, then the operating system will handle that interrupt, and after that it will fetch the next process from the queue. So these are the various states the process can visit during its creation to its termination and all, right? So it's a simple, but it's very important to know that how the process visits or the travels from its creation to its termination. What are the various states it encounters and all, right? So that way you can able. It's a very important in view of that the journey of a process from its creation to the termination. And another important thing is the process related information, whatever. When the process is created means we know that actually here there will be some specific identity, and then the program counter, the registers, memory. So when the process is created or its execution, so the process bears this information and all this information. Like a process state means here, for example, a process, as I mentioned, that in its execution, it will be in one of the states. It may be in the running state or waiting state, ready state or new state, whatever. And a process has some specific unique identity. It's not a process number. And a program counter is nothing but it's like address of the instruction in which the next instruction to be executed, right? So using a program counter, the CPU fetches the instructions, and the registers are nothing but they are used for the performing various in the execution of process, to storing the memory addresses, storing the various operands of arithmetic or the different values of in the execution of a particular process and all. So these registers, the set of registers will be used in the CPU and all. So all these registers also will are a part of the process control information, and the memory limits and all. So this process from what are the limits, that means what is the starting address of a memory and what is the last address of a memory in which the process is present in the main memory, right? And not only that, along with that, the other details, because we have seen that these details of these memory addresses and all, they will be they are available in the page tables and all. So therefore the page table addresses, and then the base address of this one, and the maximum limit of the address. So all these components come under the memory management related information. And the process also, when it's execution, it opens various files, it needs to fetch the data from different files, to write the data into different files. So therefore, when it's execution, the process had some resources. Here in this case, the logical resources like files that need to be accessed and all, maybe read from the files or write into the files and all. So all these open files. So what I mean to say is that actually here all these things constitutes the related or the control information that is related to a process and all, right? Like you can say the process state and the program counter, CPU registers, and the CPU scheduling information. That is also, it was not mentioned here. CPU scheduling information. That means that CPU schedules the process based on its priorities or various aspects and all, right? We'll see that later on. So because there are several processors available, and out of that, the CPU will will access the process in certain way, systematic way and all. So what is that scheduling criteria and all, right? So is there any priorities are there? So that information is nothing but the CPU scheduling information. using because the CPU scheduler will maintain the process in the form of queues and all. So therefore, the pointers to the queues. So all these things are related to the CPU scheduling information. The memory management information, as I mentioned that. So memory management information means, suppose if it is related to virtual memory and all, you see that CPU generates the virtual address and again to have to convert to the physical address. So therefore you require the page tables or TLBs. So all these details or related information, that is also notably memory management information and all. So that is also a part of process control information. Then accounting information. So it's required like how much of time the CPU has been utilized and how much of time the process has spent at various devices and all. What is the real time? So this way you can each process maintains its the time it's spent at various devices at various stages and all at various states. Likewise, IO status information, as I mentioned, like list of IO devices that are connected, that are allocated to a process. Because you see that sometimes the process requires keyboard, sometimes it requires the disk IO, sometimes no, we will display the device like monitor is required. So all these things, like whichever is allocated to a process and also they are like maintained by the process control block and all. We see that why this control block, why the process control block is required. So this is basically that a process control block is required because you see that the process is not allowed to, like the process is not continuously executing and all, right? The process is executing and after that the process, maybe if it requires IO and all, then it will go to IO device and then it will complete its IO and again it will come for execution, right? And not only that, when the process is executing, and it is not given access to the CPU continuously long time and all because because of the present applications, most of them are user interactive or like time sharing systems and all. So each application has been given a fixed quantum. So likewise, a very small quantum. So with that, all applications like even though have one process, only one single process runs the multiple process, but we have a feeling that like all the programs are running parallelly and all concurrently, and it will carry out in a concurrent fashion with a like can have the multiplexed in time domain. Like so in that context also the process will be switched after its time quantum. Then again after some time again it will get a chance to visit the CPU. So what I mean to say is that for execution of a process, for changing state from one state to other state, particularly when it is when it is under the execution of CPU, where, for example, here you can see the example here. Here we have a two process P0 and P1, for example, and now the P0 is executing here. So here you can see at this point of a time, an interrupt has been occurred. Interrupt has been occurred. So interrupt will occur due to several reasons. One may be that because of the time slice may be expired, or because some other device really need the service, uh, or some other maybe some error may occur during the execution. So there are several reasons for interrupt occurs. So whenever the interrupt occurs means the operating system will take over. That means operating system code has to run on the CPU and all because to handle that particular interrupt, because interrupt means some event other than the regular one, right? So whenever interrupt occurs, so during that time, before that time, a process is executing, sorry, the CPU is executing some user process. And whenever interrupt occurs, now the operating system has to take over, then the operating system routine has to be run by the CPU and all. So for that, whenever the interrupt occurs, so immediately here, whatever the current running process, it will be suspended. That means it will be stopped. So whatever the current process status, that means whenever it's stopped, at that time, the process is executing some instruction. Mostly it will try to complete that instruction. And then at the end of the instruction, whatever the state of a process, it means that whatever the contents of registers, whatever the state of a PC, and whatever the contents of other status registers, whatever. So these all known to be like a state of a process and all. So the current state of a process will be at the time of suspension, the current state of a process will be stored. It's nothing but in the PCB. So it saves the state of a process that's nothing but in the form of a PCB. That means the PCB will be updated with the present state of a process, and then this PCB, that the process whichever is suspended, and it will be stored in the PCB. It will be the PCB will be saved, right, with the current state, and then whatever the next process to be executed, because suppose the next process to be executed is the operating system, and then the operating system will be brought in, and then the operating system instructions will be executed. Then if the interrupt service routine is over, then afterwards now the next process to be run. And here, for example, the next process to be run is the P1, for example. So therefore, now the P1, that means now the P1 has to run. So therefore, whatever the PCB, whatever the state of a process P1 was there earlier, so that state of a process has to be again reloaded. It's nothing but from its PCB. Like, because now the P1 has to be run. So P1 may be executed for some point of a time. Afterwards, it was suspended. Now it is again the P1 has to run. So therefore, P1 has to run from the point where it has stopped earlier, right? So that particular state is available at the PCB of the process 1. So from the PCB means process control block. From the PCB of process 1, whatever the required information that is required, so that will be again reloaded into the registers and other things like PC and other places wherever its status is required. So all these status will be updated, and then the process 1 starts because it's updated means the PC of the process, PC of the CPU also will be loaded with the corresponding process 1, and then according to the PC, the instruction will be fetched, and then the P1 will be executed. P1 will be starts execution. And now here you can see that the P1 executes from this point to this point. And again, at this point, some other interrupt may occur, or otherwise this time slice may be over. So whenever interrupt is occurred here, immediately, whatever the state of a P1 now, the process P1, it means that the contents of a register, the PC, the next instruction to be executed, and other status, whatever is there. So the entire thing will be again saved into the process control block of process 1, like the P1. And then suppose the next process to be executed is P0 again, for example, then the state of a process P0 is again loaded into the CPU, means that the registers will be updated corresponds to the P0 where it stopped earlier, and then the P0 starts executing and all. So that way, if you look at here, when the process to be executed by CPU, some process has to be suspended or some to be like stopped, and then the new process has to be starts executed by CPU and all. So for this, for smooth running of a CPU, or for smooth running of these various processes, and also we need to have this process control block, where this process control block contains the different components control information related to a process, and so that will be saved from time to time whenever it is stopped, stopped execution or like suspended, and whenever it is again starts execution, and the status of a process or the control information of a process that is required will be again reloaded to the CPU and starts execution. And here, if you look at here, the process P0 and P1, they are in execution. And assuming that here the interrupt is a timer interrupt, that means there is no other interrupt. Only the timer interrupt interrupts the process P0 at the end of its time slot. And afterwards, the P1 will be loaded as per the next process that is available in the queue and all. Now the P1 has to be loaded. And here during this time, when the process P0 is stopped and the process P1 is about to start, there will be some time where you can see it has to handle this you need to the switching the process and all. Like you can see that the P0 has to be stopped. So when the P0 is stopped here, whatever the status of the P0, so that has to be stored into the PCB of the P0. And then the scheduler has to run here. The CPU scheduler, we need to see that what is the next process and all. So the next process will be given by the scheduler, and afterwards the operating system will brought the status of the next process. That's the P1 has to be started, P1 has to be executed. So from the PCB of a P1, whatever the desired information that is required for its execution, so that will be again reloaded into the CPU, and then the P1 will start. So when the P0 starts and then P0 stops here and the P1 starts here. So during this time interval and all, there is no useful process or useful computation is carried out by the CPU and all, because this is the like a kind of saving the contents of the previous process and reloading the contents of the process to be executed, and this is known to be context switch. So this will be carried out by the operating system and all. So during the context switch, no useful user routine will be executed. So whenever the process switching takes place, so this context switch happens, and during the context switch, the the status of a process which is stopped, that has to be stored, and then the process that need to be executed, that has to be brought in. It's nothing but the state will be again reloaded, and then it starts execution. So this saving and then reloading of the PCBs and all by the operating system, it requires some finite amount of time. And so this process is going to be context switch, and the delay that is involved in this context switch has to be minimized, because here the during this time the CPU will execute the operating system routine and all, but that's not the user program, right? So we'll try to our when you try to analyze the efficiency of a system and all, the efficiency of a system will be like how fast the user programs are executed, and what is the total times like when you load the when you start the process, when it completes, how much time, what is the response time. So all these things are important, but in the process will be switched, and in that case, the operating system will perform this context switching and all. So we try to minimize this context switch time as far as possible, so that the efficiency of the system will be improved, right? Because our target is that the user programs has to be run efficiently or with the less amount of time and all. And this is the system maintenance. Like for example, when you're switching a process and all, for a smooth running of a process without any errors and all, the process whichever is stopped, it has to be the state of the process is to be saved properly, and similarly the process to be initiated again, the state of the process to be reloaded, and it requires certain amount of time and all, right? So this is known to be context switching, and in this context also you require the process control block and all. And this process control block is maintained by is basically maintained by the kernel and all, maintained by the kernel. You can see this is the control context switch, whatever I have mentioned here and all. And the thing is that suppose if the OS is more complex and more sophisticated and all, so then it becomes more longer time, because more sophisticated means actually here it has no, more sophisticated means actually it has to very optimize in various aspects and all. So then in that case it has to do several things, like it has to uh, yeah, it has to perform more and more details and all, like it has to like store the more even it's not just a context switching, even other aspects also it has to take care. And how to minimize the context switch time. So one way is that actually here, suppose if you maintain, we know that the CPU contains some register set, as we have seen in case of MIPS, it contains the set of 32 registers and all, right? And suppose, for example, in the new architectures and all, now the things are economically available, like the chip sizes and other things, computation time and all. So in that case, suppose to minimize the context time, suppose if you use the multiple register sets instead of only one set of register in a set of registers in the CPU. Suppose if you have multiple sets of registers in the CPU, so in that case, the context switch time can be somewhat optimized. Means that when the process is stopped, you need not save the registers, the contents of registers and all, because you have multiple sets of registers. So you have when the process is switched from one process to other process, you need to change the pointer. Like right now, the current process is linked with register set 1, for example, and now the next process requires has the associated with the register set 2. So therefore, you need to just switch a pointer from set 1 to the set 2. So now the current process, whatever is loaded, so its register contents are there in the CPU itself. There is no need to be reloaded. And at the same time, the old process, whichever is leaving, whichever is stopped, you need not save it back onto the PCB and all, because they are already there. The contents are already there. And since we have multiple sets of registers and all, the CPU can switch from one register set to other register set based on the process it is executing and all. But again, there is a limitation and all. But again, the number of register sets will be again finite and all. Right? In the case of multi-programming and all, at some point of a time, if the register sets are exhausted, then at that point of a time, we need to save the contents of the register sets and all. But to some extent, if you have multiple sets of registers and all, you can optimize the context switch time. But at the same time, this is like a trial and error, not a trial and error. It's like, a kind of like when you increase the register set again, you can see that the delay times and other things also, and maintaining those register sets and also all these things also has to be matter, right? So yeah, this is one way to like having multiple register sets. You can able to optimize. You can able to reduce the context switch time because you need not save the contents of registers, because 32 registers means you have to save these 32 register contents into the PCB. You see that how much time it takes. Whereas instead, actually, if you have multiple register sets, for example, then you need not save them immediately, right? Okay, yeah. Yeah, then with respect to process, there is another very important concept known to be threads and all. So far, whatever we discussed about a process, we assume that a process have like single execution sequence. It means that a process starts at a particular instruction and it fetches the instructions one by one as the PC is incremented, right? And then it performs the sequence of execution. It performs the execution of instructions in sequence and all. And if a process executes the instructions in a sequence, right, in a single, then we know that, then we say that it's a single thread of execution. It's a single thread of execution, and it will be maintained by one PC, right? You have a PC will be there, and whatever the PC contents are there, that indicates that next instruction to be executed. So likewise, the PC will be updated continuously, and then we'll fetch the following instructions, and then it will be executed. And there are nowadays actually you can have programs where you can start execute the program from a multiple locations simultaneously. That possibility is there. That means suppose if you write the program in a proper modular way, where and these modules are assumed to be independent, right? There is no interactions between the modules and all to some extent. So in that case, you can run a process simultaneously using multiple sequences, using multiple instructions simultaneously. Using multiple, it means that what it means is that you can run the process from a multiple locations simultaneously, if possible. Suppose you have multiprocessor system is available, for example, that means a quad core system where you have 4 CPUs are available. And suppose if you modularize the code, if you modularize the program such a way that you can run the 4 modules of a program simultaneously. It means that actually here you have a single process, but it will be run, the 4 instructions of the process will be run parallelly on 4 different CPUs and all. So then you can say that in that case, we say that a process have multiple sequences of executions. So for handling this, as we know that for each sequence of execution to handle that, we have one PC will be there. That means a PC register which contains the next instruction to be executed. But here in this case, here we have multiple sequences are available in the process. You can able to run safely these multiple sequences without interaction, right? So in that case, to handle these multiple sequences, we require the multiple PCs are required, right? Because each sequence will be executed by on a separate CPU and all. So therefore, you have multiple PCs are required, right? And not only that, since we are performing the multiple sequences, right? And the multiple register sets also will be there, will be involved in that, because a particular sequence 1 in this execution. So this execution will be carried out by some set of registers, and sequence 2 will be executed by some set of registers. So likewise, you can see once you are executing a process with the multiple threads or multiple sequence of execution, then again that process control block also has to maintain the information related to these threads also, multiple threads. That means, for example, a process contains 4 threads, for example, 4 sequences of execution. And when you are running the process on the 4 threads simultaneously, then The process status are nothing but a process the information that is involving all these four threads and all parallelly. That means the thread one, it has its status, like what the PC content and then other register contents and other status information, so on. Likewise, in thread 2, it has separate sequence. It has certain some other status will be there. So likewise, when you involve the threads and all, so then the process control block also has to handle or also has to accommodate the control information that is related to the multiple threads also, right? Yeah, and so this will be the way the process control block will be represented by the kernel and all. It's like just maintain a C structure. Suppose we know that all of us, we know that how you write the structure and all, right? A structure may contain the multiple entities, right? We come across during our PDS programming and all. So if the data contains the multiple attributes and all, then you can able to define the data type as a structure. Like for example, an employee where his name, age, and other things and all. Likewise, a student. So that thing. So similar to that here also, you have a process and it has a multiple attributes are there like status, register contents, memory management information, so on. So based on that requirement of information, you can able to maintain that entire control information in the form of a structure. So each process control block will be maintained in the form of a structure and all. And all these control blocks are connected through a linked list, double linked list, right? So we'll see that the details of this in the next class and all. So we'll stop here at this point. Okay. Yeah. So if you have any questions. Yeah. If you have any questions, those who have class, next class, then you may leave.